Okay, yeah, so hello everyone, I'm Pria. I'm a second year grad student in Ephraim Steinberg's group. And today I'm going to be talking to you about optical metrology using few-photon states. For those of you that aren't super familiar with our group, we have two labs. One lab works on cold atom experiments and the other works with single photon experiments. So I'm going to be telling you guys a bit about one of the directions that we're interested in the photons lab. So oh no. Doesn't let me change this. There we go. So I'm going to tell you about two different quantum multi-parameter estimation experiments that we either have recently completed in our lab or are currently doing in the lab. I'll first start by trying to give a bit of motivation about what quantum metrology is and what quantum parameter estimation is. And then I'll move on to telling you first about an experiment where we generated what we call the tetrahedron state, which is a optimal 4-photon state for parameterizing a rotation in polarization space. And then I'll tell you a bit about what we're working towards doing now, which is creating a 2-photon state, which is also optimal for that same task. So quantum metrology is a subfield of metrology which concerns the study of measurements and has many applications in major fields and applications in things such as gravitational wave detectors like LIGO, magnetic field sensing, and systems such as atomic clocks and things where you basically need high precision measurements. And the crux is that we can basically use quantum effects to give us higher precisions in measurements than what we would normally be able to achieve by just using classical approaches. And this can also help us understand the best way to measure multiple transformations that are generated by observables that don't meet with each other. And this is where the multi-parameter estimation problem comes in that I'll talk about in the course of the presentation. So I'll go through a small example of parameter estimation just in the case of a single parameter to kind of give you a basic idea. So say you want to estimate a particular parameter, and there's basically two main limits that we come across in metrology. The first is known as the standard quantum limit, where the error in our parameter scales as 1/√n, where n in most cases is the number of measurements that you can do, and also in many cases it's equivalent to the number of particles you have in the system. And typically we want to aim for what is known as Heisenberg scaling, which is the best scaling that quantum mechanics allows us to get, and it's where the error in our estimation scales as 1/n. So there's a quadratic improvement there. So we typically want to aim for that. And the example I can show you this, the kind of power of quantum metrology is in the estimation of a phase phi between two arms of an optical interferometer. And it turns out that if you have a system of n photons that you can send in for your input beams, for example, there's a particular quantum state that we can send in that is the best state for this task of estimating this phase, because it's most sensitive to that. And it's known as a noon state, which, if you're not familiar with it, can be a bit weird, but it's basically called a noon state because if you write it out like this, it kind of spells the word noon. It's a superposition of sending all of your n photons in through path A and none in mode B, and then vice versa, all in B and none in A. And but this is just the case for a single parameter estimation. If we want to estimate multiple parameters at the same time, things can sometimes get a bit more complicated if we have transformations that are generated by observables that don't commute with each other. Previously, people thought that if you have a particular quantum state that is really sensitive to measuring a given transformation, it naturally comes with a decrease in sensitivity in measuring other transformations. For example, if you were to use the noon state that I just showed you to measure a rotation around a particular axis, it will be optimal for just one axis, and will have zero sensitivity to rotations around the other axes. It turns out that this is not always true, and this kind of misconception was cleared up by a special state known as the compass state, which is basically a superposition of 4 coherent states. This is what its Wigner distribution looks like, which is kind of a quasi-probability distribution, and it's called the compass state because we have the 4 coherent state blobs at 4 points of a compass. And the special thing about the compass state is that it is super sensitive to measuring displacements in both position and momentum, and we all know that those don't commute. So this kind of solves that problem. And recently in our lab, we experimentally generated a kind of analog of this state but for measuring polarization rotations, and we called it the tetrahedron state, and I'm going to tell you a lot about that now. So for the task of measuring rotations on a Bloch sphere, which is how we kind of describe polarization rotations, the tetrahedron state is a state consisting of 4 photons, and it's the optimal state that gives us this Heisenberg scaling if we want to parameterize a particular rotation. And it gets its name from the fact that if you are to look at its, you can't really see, but there's like a sphere here. So this is meant to be on a Bloch sphere, but you absolutely can't see that at all. I apologize. If you were to plot this state on a Bloch sphere using its what's known as its Majorana representation, where each of these kind of vertices correspond to a photon, you have 4 photons, and they're kind of distributed in this equilateral, regular polyhedral shape. With 4 photons, that's going to look like a tetrahedron, and that's where it gets its name from, because it has the same rotational symmetries and properties as a tetrahedron. And I don't have a lot of time to explain properly what the Majorana representation means, but it basically is kind of corresponds to the zeros of the Husimi distribution, which is where each of these points are, and they are equally segregated on the surface of the Bloch sphere. And this is the tetrahedron state. It consists of 4 photons, which is the lowest dimensional of this whole class of states that have these representations in higher orders. So for higher photon of this. So we attempted to make the lowest dimensional of these states using 4 photons. Okay, so what does a multi-parameter estimation experiment look like in the lab? We can break it down into 3 simple steps. We first have to prepare the quantum probe state that we're trying to use to most sensitively estimate the parameters that we're interested in. We then have to make our state interact with these parameters in some way. So in this case, this would be making it undergo polarization rotation, some change to its polarization that we will then measure. And we'll see how well we are able to estimate the rotation. So I'm going to talk to you just about the first of these 3 stages in terms of the tetrahedron state, how we went about preparing that state and characterizing it. Okay, again, the Bloch sphere part of this diagram is not showing up on the screen, so I apologize if it's not super clear. I'll just try and give a quick conceptual description of how we make the tetrahedron state in the lab. So again, this is the kind of Majorana representation depiction. We basically create a 3-photon Luna state. So that's the same thing that I introduced at the beginning of the talk, but this time n is 3, we have 3 photons. And then for our 4th photon, we interfere it with a single horizontally polarized photon. And that creates our 4-photon state. And this is if you were to write it out in terms of annihilation and creation operators, for the 2 modes, horizontal and vertical polarization, that's what region B means. Acting in the vacuum. This basically it's Majorana representation on the Bloch sphere. Yeah, I'm sorry if it's not super clear. I reduce the picture. What this looks like in a lab, I won't spend too much time talking about this because it's quite complicated. But we this is the experimental setup that we use, and I don't know why some of the text is gone from the legend. Sorry, but so we create the new state here. We then have a single photon that we create separately through the Howard approach, and both of these we generate from a pulsed laser source, and we use spontaneous parametric down conversion sources to create the single photons. That's the SPVC crystal label on the diagram. Then we interfere both of these 2 separate states together in the Sagnac interferometer, and then we can do tomography on our state and characterize the tetrahedron state that we created. Okay, so how do we characterize it? We perform state tomography, and we do this by using the fact that if you consider just the polarization degree of freedom of a single photon, you can effectively think of it as being a spin-1/2 particle. If you use just any 2 orthogonal polarization basis vectors, like horizontal and vertical, for example, you basically can think of it as a spin-1/2 system We have 4 of them in the tetrahedron, so it's effectively a spin-2 system, and we can decompose its Hilbert space into this direct tensor sum. This is all to say that we don't really want to worry too much about these spin sectors. We expect that most or all of the population will be in this fully symmetric spin-2 subspace. So that's what we look for when we do our characterization, because ideally all the photons are going to be indistinguishable and completely identical to each other, and that means that they're constrained to be living within this spin-2 sector, which is the fully symmetric sector. So how did we do this? These diagrams are density matrix reconstructions from tomography. The first one up here shows the kind of those 3 different spin sectors that we can decompose our state into, and we expect, like I said, we expect the tetrahedron to be living within this rho symmetric spin-2 sector, and where you see rho experiment rho x, that's the full experimentally generated tetrahedron state that we created in the lab, and we managed to get most of the population, around 87%. Was found to be within that spin-2 symmetric sector as we expected. But unfortunately, there were still some non-negligible populations in the spin-1 sectors, which contribute to the relatively low fidelity of the state that we created in the end. But I can talk more about that later and how we can improve it. But overall, most of it is where we expect it to be. But all is not lost. We can see some qualitative features of the ideal theoretical tetrahedron state that we aim to generate. So in the top left, these are also supposed to be the Majorana depiction on the block sphere. So it's a bit difficult to see, but the red points are the ideal theoretical tetrahedron state, and the blue are the one that we created. So they're relatively close. I'm going to talk mostly about what we call the main eigenstate of the tetrahedron state that we created. This is just because the entire tetrahedron state that we created experimentally is a mixed state, but we look mostly at its eigenstates, and particularly one that has the largest eigenvalue that is created most of the time. And that particular eigenstate is created with 92% fidelity. That's the one that's plotted on the top left, which is really good. However, we only create it 49% of the time, but we can basically say that our way of creating this tetrahedron state works half the time at creating almost an optimal tetrahedron state. And you can see the features that you expect from the ideal theoretical tetrahedron state in the Spickman distribution on the top right are present in the Wigner distributions of the one that we created. There's 4 plots because we have kind of viewed it from the 4 different vertices of the tetrahedron state that we created, but they should all be identical to each other and to the top right one ideally. They're not perfect, but there's definitely the features that we aim to see there. Okay, I have to give a quick interlude about a metric that we commonly use to determine whether our state is optimal and what we mean by that. So we use a quantity called the quantum Fisher information to kind of quantify this. Again, I don't have a lot of time to go through absolutely everything, but basically, if we know the quantum Fisher information, we can calculate, let's calculate a bound on the covariance between all the parameters we're trying to estimate. And ideally, we want to minimize this quantity so that we have a very low variance with our estimation, implying that we can estimate it very well. And one particular bound that we use is known as the quantum Ring-Arrow bound, and it bounds the covariance matrix between all the parameters from below as the inverse of the Fisher information matrix. Yeah, so in order to conveniently be able to optimize this bound, we have to convert it from a matrix inequality to a scalar inequality. And we do this by using what we call a cost matrix. And it basically weights each element of the covariance matrix accordingly to a choice that you can make. Typically, we use just the identity for the cost matrix, but it kind of comes from the part-time metric, so it depends on your system, but in this case, it's very simple and straightforward. Again, I can't go into that too much right now, but basically you have this scalar bound that we then want to optimize by taking the this these two matrices. And so then what we did was compare different values of this scalar bound that we're hoping to minimize as much as possible in order to get the most information about the state, to different types of states and how they perform at estimating the polarization, rotation, and compare them to our tetrahedron state. So some other common strategies people use are to try and use the noon states that I talked about before to measure rotation. But as I mentioned, they are only optimal for measuring rotations when they are aligned to a particular axis. And if you want to get around this problem, you can prepare kind of 3 different batches of noon states aligned with each axis that you want to rotate around. And then they work fine. And you get the Heisenberg scaling as you increase the photon number, as you can see with this orange line. But it's slightly above the how the platonic states perform, so the tetrahedron state and other polyhedral states, because you have to do it 3 times. So there's a factor of 3 that you currently can't scale there. We also compare them to what are known as spin coherent states, which is just all the photons polarized in a particular mode, and they perform quite a bit worse than the other 2 approaches. And you can see that they don't scale with the same slope, which is, so this will be the kind of 1 over n scaling that we're looking for, and this is the 1 over root n. So in general, we also see that we can use these platonic states to achieve the Heisenberg scaling. As you increase the photon number, your scalar quantum Kramer also decreases. And the 2 data points that are in black there are the ones that we generated in the lab, the tetrahedron state that we generated. We didn't physically use this to estimate rotation. This is just a simulation, but we calculated that it performs its main experimental album state. It performs very well, very, very close to the theoretical value of the ideal tetrahedron state. And the entire density matrix is slightly worse, but it performs better than the spin coherent state approach, which is good. So just to sum up what I told you so far about the tetrahedron state, so we demonstrated an experimental way to generate this tetrahedron state in the lab. As I mentioned, the fidelity of the state that we created could be improved. Most of the noise comes from when we generate the through photon noon state, we interfere a squeeze state from down conversion with a weak coherent state, but that coherent state will have higher order photon terms in there, and they can contaminate the state and give us more than the 3 photons that we're aiming for in the noon state. And also, we could increase the indistinguishability of the single photons that we use throughout the experiment. And we could achieve this with just better sources and detectors. However, at the proof of concept level, at least, we've created a state that is that shows very like a large amount of the features and symmetries of the optimal theoretical tetrahedron state. So now we're asking a question: what about photon numbers that don't correspond to these regular polyhedral platonic solids on the Bloch sphere? So this is numbers that you can't represent as the minor representation of these nice regular polyhedra. So numbers like 2, 3, 5. We've started thinking about is there a 2-photon state that also shares these super sensitive and nice symmetric properties as the tetrahedron for estimating the polarization rotation. So we've been building I'm skipping ahead. This 2-photon state could look like this on the Bloch sphere. We have 2 photons here and here, and we can tune this kind of angle between them, between going from both of the photons horizontally polarized in a spin coherent state to the maximum entangled state. And we can physically tune this angle just with a wave plate in our experimental setup, which I'll show you in a minute. And we can find what this optimal angle is to estimate our rotation. So the setup looks like this. So this is the first of the 3 stages. We prepare our state. We interpret 2 single photons at a beam splitter. I haven't shown the source of the photons, but they come from a double pass spontaneous parametric down-convergent source. We then make the state undergo a polarization rotation, so we pass it through a polarization controller, and then we'll do state tomography here, which is the measurement part. So this is what we've been working on recently, and yeah, this brings us to the end of my talk. So just to sum up, I told you a lot about the tetrahedron state, and that's the optimal full-photon state that you can use to simultaneously estimate all the parameters that describe a rotation in polarization space. And I also talked briefly about the progress that we've made towards setting up an experiment to do a similar thing, but using 2 photons, and use that to estimate polarization rotation. Yeah, so again, most of the content in this talk was from Hugo Ferretti's PhD thesis, and he's the student who graduated a couple of years ago and led the experiment working on the tetrahedron state. And I just want to say thanks to everyone in the Photons lab who worked with me on these experiments. So that's Fatima, Jan, Maggie, and Jerry. Thanks.